nothing like perfect. Okay, when you focus on this area with microscope, and zoom it, you will see something like this. Okay, I'm just exaggerating it. These two surfaces look like this. Okay, this is surface 1, surface 2. Okay, and in between these are the wavy surfaces, and in between these surfaces there is a void in which fluid is there, mostly air. And we know that air has very low thermal conductivity, so it will increase the thermal resistance and decrease the conductivity, heat transfer through these two materials. So it is very difficult to transfer the heat from 1 to 2 if air is there and surface roughness is very high, that it forms a pockets of air in between the two surfaces. In electronics you will see that there is PIM, interface material. Interface materials are used. For example, elastomers have high thermal conductivity as compared to air. They are placed in between these gaps where air is there to increase the thermal conductivity and the heat dissipation rate of electronics, and it is widely used in electronics cooling in industry. So to overcome this challenge of, so because of this air, extra resistance is placed in between the two surfaces. Here we are saying that there is no resistance, there is resistance by the material 1, resistance by material 2. But what about the interface? Interface is also imposing some resistance because of presence of extra material, which is the air in between the two materials 1 and 2. So we have to consider that also. So if we consider the case for series, okay, so let's say T1 is the temperature at this, and Tc1 is the temperature at the interface, but because of the contact there is resistance is imposed for the heat flow, and there is temperature drop on the interface 2, and then after that temperature drop in the material T2. And this drop of temperature is because of the contact between material 1 and material 2, and this resistance that is means emerged out of the contact of two materials is called contact resistance. Okay, so if we draw again the resistance diagram, T1, then Tc1, then again we have to put one more resistance, which is the contact resistance. Keep in mind, we can decrease that resistance by placing the material, like I talked about the interface material, okay, to decrease that thermal resistance so that these two temperatures have almost same value. If these two temperatures have almost same value, that it means that contact is near to perfect. Okay, this can be done by increasing the pressure between the two surfaces when they are joined, first, and number 2, if we can reduce the surface roughness value, that the undulations are like this. Let's suppose undulations are like this, so air is very less if the undulations are less. Okay, so extra contact resistance has come, and the resistance by the material too. So when we calculate the heat transfer for this case, we have to consider the temperature drop T1 minus T2, and then sum of all the resistances. Okay. So contact, this was the concept of contact resistance. We can note it down in words. In practical cases, when two surfaces are joined, with each other, then due to roughness, some cavity is formed. Okay, and in that cavity, some fluid is trapped. And due to low value of thermal conductivity, low value of thermal conductivity of fluid as compared to solid, there is additional resistance. There is additional resistance which comes into picture for heat flow. As a result, temperature drop. Down at the contact surface. Okay, so this is the concept of contact resistance. So from next class we will find the temperature distributions for one-dimensional cases like plane wall, cylindrical and spherical. Okay, so for simplified cases we will find. Thank you.